This time we're moving past series and everything series sequences, and we're moving on to the other part of the class, which is vectors, and more specifically moving on to graphing in 3D planes. So what is a point on a line? So a point can be, so let me draw a graph that we're usually used to seeing. So something like this. So the point 1, 0. Let me get some labels. 1, 2, 3, 1, 2, 3. So in usual previous classes, the point 1, 0 would be x is 1 and y is 0. So it would be right here. And then something like 3, 2 would be x is 3 and y is 2. So these are 2 points, 1, 0, and then 3, 2. These are the 2 points on this graph. And now we're moving on to, this is 2D because it's only 2 dimensions. So this is the x and the y right here, x, y, x, y. Now in this class, we're going to moving on to 3D graphs, planes, 3D, what did I say, surface, or not surface, just a 3D environment, which is the real world we live in right now. And that would look, instead of just x and a y, it'll have an x. I mean, this is a new one, a z. Then you can draw it however you want, either straight, or I'll draw it separate ways to show you the different ways it can be drawn. A y, and then an x. And in this class, you can draw it different ways, but usually the x is like facing us. It's this part. So if you visualize this in the 3D plane, imagine this part is facing you, and this part is behind you, and this part is going up, this part is going down, and this part is going to your right, and this part is going to your left. And that's how you can visualize this 3D graph in our actual real world. So in this, instead of just x and y as the 2 variables, there are 3 variables now. This is the y, this is the x, and this is the z. And in this kind of, in the 3D instead, the points shift from being just 2 different commas. So instead of 1, 0, we have to do 1, 0, 0. Because now there's an extra variable, the z, so this would be x, y, like the previous one, but now there's an extra z back here. And to plot this on the graph, would go, this is the positive part of x. I'm not going to do negatives, just the positives. This is the positive part of y, 2, 3, and then this is the positive part of z, 1, 2, 3. So 1, 0, 0 would be somewhere in space, where in the x it's 1, so along this axis it's 1. Along this axis, it's 0, the y, and along the z-axis, it's also 0. And then this would be the point right here. So I'm gonna get rid of all the lines. And then the point 1, 0, 0 would be right here. Actually, no, right here. It'll be right here on the x, wait. It'll be right here on the x-axis, because that's where x is 1. And then that's where z is 1, and that's where y is 0. And then a different point, let's say I'm gonna do one in space where it's like 2, 2, I'll do 2 different ones, 2, 2, 2, 2, 2, 0, and 2, 2, and then 2. So the first one, this one right here, it'd be at x equals 2, y equals 2. And then if you can visualize this in space, it's going to be on this plane where z is 0 at this level. So it's going to be right here. And then the other one, 2, 2, 2. It'll still be that 2, then 2, but then it'll be up higher. So it'll be on this plane as well, but higher. And it'll be at where z is 2. And that's how you put points on 2D and 3D. But now in different, on the points, imagine if you had, let's say, you didn't have a z, and it was just, the point was just given 1 comma 0. Right here you didn't need a z, so like I'm gonna do it in 2D first. So if you had a point where instead of 1, x is 1 and y is 0, they just tell you there's no y and it's just x is equal to 1. Since this, when you constrain one of the variables, when there's no y and you only have to do x, the whole thing changes. It's no longer a point and it becomes a line. And we all know what the the x equals to 1 line is. It's just where x is equal to 1. So right here, x is equal to 1. And this whole line up here, x is always 1. Like the y changes, but since the y isn't constrained, that means that this whole till infinity, from positive infinity to negative infinity, the x is always going to be 1 in this place. So that's what x equals 1 would look like. So let's move that over to the 3D graph. If we do just x equals to 1, like we did over here, and there are no y's, so y isn't given or it's not constrained, and z isn't constrained as well, what we're going to have is, so the x can only equal to 1, and x is equal to 1 at everywhere that goes here. But then since the y can be anything, so the y can be all the way from here to here, and the z can be anywhere from here to here, it's so the z can be negative infinity to positive infinity since it's not constrained, and the y can be negative infinity to positive infinity. So what that's going to come out, it's going to look like a shape like this, where it goes all the way to infinity, all the way to negative infinity, and then goes down all the way from infinity to all the way to negative infinity, and then this also goes down here too as well, like this, and then let me finish it. And what this is called a plane. This is a plane where an x is equal to 1. And why it looks like this is because, like I said earlier, z can be anything from negative infinity to positive infinity, and then y can be anything from negative infinity to positive infinity. And this, when this is a plane, this means that the only thing that holds true is that x is always 1, because x is always going to be 1. But then the y can be anything and z can be anything. And that's what happens when you only have one constraint, which is the x. So that means only one of them is constrained. One of the 3 points is constrained to a particular place. This is stuck at x equal to 1. The x can't be anything but 1, but the z can be anything and the y can be anything. And then when you have 2 constraints, so let's say x equals to 1, and let's add y is equal to, what can y equal to? 2, I don't know. What this would look like is, since, and remember, if they don't give a z, let's say z is not constrained, so z can be either positive to negative infinity. What this would look like is, let me erase these. What this would look like is, so if the x is always going to be 1, it's going to be the same, where it's going to be on this line of x equal to 1, and then y is equal to 2. So it's going to be, it has to meet these 2 criteria where x is always 1 and y is always, and let me draw that y again, and y is always 2. And for it to meet that criteria, what happens is it has to be a line. So the x is always going to be 1, it's going to be a line up from 1, and then the y is always going to be 2, so it's going to go up like this. It's going to be a line where the x is always 1 and the y is always 2. So right here, it's at 2, y equals to 2, and it's at x equal to 1. And that's a line. And look, as you can see, the z is not constrained, so it can go all the way from negative infinity all the way up to positive infinity. And that's what, I'm gonna write it down. When there's one constraint equals to a plane, and 2 constraints equals to a line. And this is in 3D, remember, in 3D. So now let's move on to vectors. So a vector is just going from one place to another. It's literally a line in space or in 2D. So first I'm gonna do it on 2D. So imagine I start at imagine I start at, let's say, this point over here where x is -3 and y is 1, and I move to this point, a random point, where x is 2 and y is -2. This is the easiest way to get there, or the fastest way I'd say to get there. It's going to be in a straight line from that point to that point. And this is simple as short. It's a vector. That's how easy vectors are. I mean, the idea of vectors are easy to understand, but then what makes the chapter hard, or the whole topics hard, is what, like manipulating vectors. But vectors literally from a point to another point. And right here, these are two different points. So technically they're not vectors, but to get vectors, you just go from the point, so you just subtract the points. So from this point minus this point gives you this vector. So it's just going to be 2, -2 minus -3, 1. It's going to be the x values subtract each other and the y values subtract each other. So 2 minus 3 is 2 plus 3, so 5. And then -2 minus 1 is going to be -3. And then we use different, instead of a normal bracket, we use this kind of brackets. So like this. And then this is no longer a point, this is now a vector, which is describing this line that goes from there to there. And what it basically said is that it went 5 to the right and down 3. And it's the same thing here. So it went from 1, 2, 3. Wait, did I do that math right? Yeah, it went 5, so 3 here to 0, and then 2 here to 2, and then that means it went to the right 5, and then -3 means it went down 3. So it went 1, 2, 3, down 3, and then 5 right. So 1, 2, 3, 4, 5. Yeah, I don't know why that was confusing me. And this is not important to know right now, but later on in the chapter, this is going to be important, because if you remember slope, the slope of 2D, it's basically the x over the, slope, I think slope is the y over the x. So the rise over run, yeah, the y over the x, what it is versus what it ran. So for this one, it will be the y, which is -3 over 5. And that's what the slope is, the slope of a line. And you can get that from the vectors, because that's what the vectors tell you. So for 3D, it's practically the same thing, but now instead it's in a 3-dimensional state. So I'm going to do something similar where the points, I'm going to do it in positives. So the point 3, 1, and then 0, and then it goes to the point, 0, what y should I use? 0, 0, and then 2. Actually, let me use 0, 0, 0, which is just the origin first. So this is the origin, and then 3, 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. So 3, 1, 0 would be 3 here and 1 here. So it would be somewhere around here, and then this is the origin. And then the line from the origin to the point, that's a vector. And that's usually the forms of vectors. Like when they give you the vector would be, first let's find the vector. When you subtract these two, gives 3 minus 0, 3, 1 minus 0, 1, 0 minus 0, 0. This is a vector for this line. And usually when you get a vector like this, you can assume that it came from the origin to this point. So then, like, you see how these two look exactly the same but different notations? You can't misplace. A point is not a vector. That's an important thing. You gotta know that this is a point, but then this is the description of how to get from the origin to that point, and that's a line. It's always going to be a line. And then another important thing to know is that vectors aren't stuck in space. And what that means is that just because it goes from 3, just because this is a vector doesn't mean it has to have started from the origin. So I'm going to give you another set of points. So like this, 4, 2, 1, and it started at 1, 1, 1. So that means it started at 1, 1, 1, so up here, and it went to 4, 2, 1, somewhere around here. Let me do that better. Yeah, it went somewhere around there. If you do the vector for these 2 points now, 4, 2, 1, and 1, 1, 1, it starts at 1, 1, 1, and goes to 4, 2, 1. Right here. Although I didn't draw it as good, as you can see, these two are the same exact line, but just in a different spacing line. And if you find the vector for this, it gives you 4 minus 1, 3, 2 minus 1, 1, 1 minus 1, 0. These two are the exact same vectors. And what that means is that vectors aren't stuck in a place. They're not constrained to a position. Like how points are constrained to the particular point that's represented. The vectors can move around anywhere in the point, anywhere in space. Then they retain the same vector even though they switch position. And that's an important trait of vector that is going to be used on later in the class, is that vectors aren't restricted in space or wherever they are. And they can move around. Like same goes with this one. This vector can move to like somewhere here. It's still going to have the same equation for the vectors, but it's just going to be describing the difference between two different sets of points.